Welcome to part 2 in our discussion of logistics growth. We're still working for the Fish and Wildlife Division, and we're still talking about the number of fish in a lake. Now, our growth rate is still the same. Now, just like before, I'm going to rewrite this by factoring out that P over 6,000, just so I can work with it. This becomes P over 6,000, and that's going to leave us with just 18,000 minus P. The only difference is this time we're starting with an initial population of fish of 10,000. There's our initial population. Now, what doesn't change is our carrying capacity. Remember, that's my carrying capacity, the 18,000. So as time goes off to infinity, again, in this lake, the most number of fish we'll ever have is 18,000. Our range will change, though. Remember, initially our range was at 4,000 from part 2 in example number 1, but now we're starting with an initial population of 10,000, and we're going to go all the way to 18,000. Remember, this is a hard bracket because I'm starting with 10,000 fish. Solved here because it's asymptotic, right? Now, the first question, same as it was for part C. Where is the curve increasing or decreasing? No sense reinventing the wheel. We already have our critical numbers from example number 1 in part 2. The population, the critical numbers are P is 0 and P is 18,000. So when I set up my first derivative test, dP dt, and there's a P. When I plug in my numbers, remember 0, 18,000, but this time I'm starting at 10,000. Remember, I don't want anything in between 0 and 10,000. I already have it all. I already know what's going to happen. Nothing, because I'm starting with 10,000 fish. Now again, like in part 1, if I pick a number between, like let's say 12,000 fish, positive, positive. So this is going to be positive, positive, so it's increasing. So we know that the population, just like before, that the population of fish is increasing on that domain. And I'm going to go and name the domain 10,000 to 18,000, and that is because the derivative dP dt greater than 0. Now, what's going to happen though, let's talk about when we do the concavity of the graph. Remember, this is our second derivative, so we can use our concavity test. And we already know that the second derivative from part 2, example number 1, that the second derivative is 1 over 3,000 dP dt, and that gave us 9,000 minus P. So remember, these are called possible points of inflection, are going to be P equals 9,000, 0, and 18,000. Remember, we get that from above, right? dP dt, we know that's going to be 0 at 0 and 18,000. Don't need to reinvent the wheel because we already have those. When I write out my logistics growth, when I write out my second derivative, check here, I'm going to go 0, 18,000, but remember I'm now starting at 10,000. I don't care about anything before that. Now, what's kind of interesting, since we don't care about anything before that, notice, where does my point of inflection lie? In the region that's not even covered in our domain, in our range here, so we don't have to worry about it. All I have to do is pick any number in between 10,000 and 18,000. So let's go again with 12,000. It worked for us before. And if I plug it in, now recall from part 2, dP dt is positive. We get that from up here. We already said that 12,000 dP dt is positive. I just have to plug to the second one. 9,000 minus 12,000, that's a negative number, so this is going to be concave down. So this is going to be concave down on the interval, soft bracket, 10,000 to 18,000, and that is because the second derivative is less than 0. So what's that telling us? That the population of fish, in this case, is still increasing. It's still increasing, but it's increasing at a decreasing rate. And if you work for the Fish and Wildlife, you can tell it to somebody, hey, if we start with 10,000 fish, yeah, well, they're going to be increasing, but that population is going to be slow, that rate is going to be slowing down. Now, do we have a point of inflection? And of course, this one, the answer is no, not in this case, and that is because P equals 9,000 is outside of our range. Remember, our range was from only 10,000 to 18,000. So there's going to be no point of inflection. I was thinking, there's no point to this. Math humor. Now, if we wanted to sketch this, here's time, here's our population. We're now starting at 10,000. Here's 18,000. There's our asymptote. It's going to be concave down the whole way. Now, if we compare that to the original, remember, here's my original graph right here. If I compare this with the original, let's say here's my population of 10,000. So it's basically we're moving our population axis over to, well, 10,000 meets our population graph. And we can kind of see it's only going to be concave down. Interesting, huh? So there's a lot of relationships here. Now, what happens if we start with a population above the carrying capacity? And that's example number 3. Notice we're starting at 20,000. Then my initial condition is above my carrying capacity. So let's think what happens. And let's see if we can prove it. Now, again, I'm going to write out my formula. By factoring it, dp dt, I get P over 6,000, and that's going to give me 18,000 minus P. Doesn't change. So remember, this is my carrying capacity, that 18,000. So the most the population will ever be, as time goes to infinity, 18,000 fish in that lake. What's going to be our range? Well, the range, now, be careful. I am going to switch it this time. The 18,000 goes on the left side, and it's a soft bracket because that's where my asymptote is. And it goes up to 20,000, and that's a hard bracket because that's where I'm starting from. Okay, so we kind of switch things around a little bit, so be careful with something like that. Now, sometimes people say, can we go 20,000, 18,000? Technically, you can. It just looks weird. Now, is the graph going to be increasing or decreasing? Now, we have to check this one again. Now, be careful. We already have our critical numbers. We know P is 0 and 18,000. We get that by setting, remember, dp dt equal to 0. Now, so, if I do my sign test, there's 0, there's 18,000, but remember, I'm going to 20,000. dp dt and p. This time, I don't care about anything before 18,000 because I'm not starting there. So what do you think is going to happen? The fish has the population, you would think, because we're starting with 20,000, our carrying capacity 18,000, this should be negative. So let's see if it works. This should be negative because we have to go to our carrying capacity. So if I check it out, I'll pick a population of, let's say, 19,000. Plugging it in to my derivative, of course, P 19,000 over 6,000 is going to be positive. I don't know what it is, but it's positive. But if I take the 18,000 minus 19,000, that's negative. It's decreasing, just like we thought. Good job, everybody. So the population of fish is decreasing on this interval of 18,000 to 20,000. And that is because the derivative told me so. We don't ever say it that way. The first derivative is less than 0. What about the concavity? Well, let's check that. Second derivative. Now we already know what the second derivative is. Remember, I'm going to go ahead and write it out again. Give me a second. I know normally I'm talking, but I'm quiet now. Our possible points of inflection do not change. They are P equals 0. Whoops, 9,000, I'm sorry. And remember where this one was? 0 and 18,000. Okay? Where, remember how we get to 0 and 18,000? It's where dp dt is 0, which we have in part C. These come from part C, if you must. So if I draw my concavity test here, 0, 18,000, and there's 20,000 fish under the sea, dp, dt, the second derivative, p, don't care, not there, ha ha ha. So I pick a number, 19,000 worked for us last time, plug it in. Now be very careful. In this case, dp dt is negative on the domain, on the range here. I'm sorry, the range. It's negative on the range. And that's because up here, we proved it up here, it was negative. So my first factor is going to be negative, always. But if I plug in 19,000 over here, I get 9 minus 19,000. And what is that? Also negative. Now, we should hopefully know that this is going to be concave up, because remember, there's an asymptote here. This is an asymptote, which means I'm approaching it. And if you think about it, if you're starting above an asymptote and you're heading to the positive direction, you have to head towards the asymptote. You're not going to go down like this, you have to cross it. Asymptotes kind of direct behavior of a function. The asymptotes tell me it should be concave up in this situation. So this is only going to be concave up, and it's going to be concave up on the domain 18,000 to 20,000, because the second derivative talks to me and said so. It was going to be positive. There's your answer. Now, do we have a point of inflection again? No. And what's the reason why? The same as example 2. Okay? Because our point of inflection would have been at 9, because 9,000, when the population 9,000 is outside of our range. And remember, our range was 18,000 to 20,000. Now, could I graph this? Yeah, we already kind of graphed it. We're starting now with 20,000, and we're going to 18,000. There's my asymptote. And this can look something like this. I hope you guys enjoyed it. I know this is a little bit long here, but these are kind of fun to do, and I'll see you guys later. Thank you. Bye-bye.